To lesson 1.1 in pre-calculus. We're going to take a look at example 5, finding the domain algebraically. So we have some different functions, and basically there are three things that you need to remember when you're finding the domain algebraically. You have to be careful for three things in particular. Fractions. If there's a variable in the denominator, then we know that this denominator is not allowed to be 0. So in this case, x cannot equal 0. But if there were other expressions around this, or a factor of x minus 1 down here, then it would be the value of 1 that would make this 0. So x could not equal 1. So fractions are one thing. The other thing is radicals. Because we're doing square roots, it would have to be even root radicals. Even root radicals like square root or fourth root. So for example, cubed roots, it's okay because you can take the cubed root of negative 27 and that's negative 3, because negative 3 cubed is 27. Also, so when we have a radical, you can even take the square root of 0, that's fine. The square root of 0 is 0. You can do the square root of 4. You cannot do the square root of negative 4 without getting an unreal number, that is 2i. When we're talking about domains, we're talking about real number domains. So in this case, anything under the radical, which is called the radicand must be greater than or equal to 0 when you're considering your domain. For a fraction, when you're considering the domain, the denominator is not allowed to equal 0. It can be any value, fractional, decimal value, that's fine, but it cannot equal 0. The expression in the denominator cannot equal 0. And then the third one is a combination of these. Fraction / radical combo. So I actually have an expression, doesn't matter what polynomial expression or just number that I have in the numerator, but I have some expression down here that involves a radical, and the radical is in the denominator. So in this case, the radical denominator, or the radicand from the denominator, we can see that it can't be equal to 0, and the radicand has to be greater than or equal to 0, but because it's a denominator, it cannot equal to 0, therefore it must be strictly greater than 0. This is a summary of what we would have seen in our exploration. So I'm going to do some specific examples with this right now. We have the following functions. I'll give you 3 examples. There's also a few in the book. Here's the first one. One with a fractional denominator. Example 5, I'll call this A. It doesn't match your book exactly. So on this we have 3t squared over t squared minus 1. Well, because luckily this doesn't have a radical or a radicand, but it does have a denominator, and we know that that denominator, t squared minus 1, is not allowed to equal 0. We need to solve this. With this particular polynomial, we can factor, or we could solve by adding 1 and taking the square root. I'm going to add 1 and take the square root for now. So when I take the square root, t equals plus or minus 1. But remember, this is what t cannot equal. If t is 1, then that would become 0. 1 squared is 1 minus 1. Negative 1 squared is 1 minus 1 is 0. So those are the values that it can't be, but now we have to put this in interval notation. What this means in terms of my number line, sometimes I have students draw a number line to help them. Negative 1 and 1 cannot be solutions, but anything between them, anything to the right, anything to the left is. So now for our interval notation, we can go from negative infinity all the way up to, but not including negative 1. Well, that's why we use the parenthesis. We can go from any numbers between -1 and 1, but not include either of those values. And we can go from 1 to the right infinitely through all numbers. So this is the domain for this expression right here. All values, it's basically all real numbers except for plus or minus 1, and there it is in interval notation. For our second example that is like this, but this time a radical, remembering that the radicand has to be greater than or equal to 0, we have the expression the square root of 4x minus 1. So we know that the radicand, what's under that radical, if it's an even root, and this is a square root, so it is, we have to set that greater than or equal to 0. Well, that means that when I solve for x, now if I were to divide by a negative, that would flip the inequality, but I'm not, just dividing by 4. X has to be greater than or equal to 1/4. As long as it's greater than or equal to 1/4, then the smallest this number could be would be 1 minus 1, which is 0, and the square root of 0 is 0. So we would have a real number output for this real number input. So for our domain for this, x is greater than or equal to 1/4. You can do that on a number line if you want. I'm just going to put the domain for this is including x equals 1/4, and then continuing on infinitely in a positive direction. Our last example is one that has a radical in the denominator of the fraction. So we have x minus 5 over the square root of 2x minus 3. So this will be 5c, an example of a fraction that has a radical in the denominator. Because it's a radical, the radicand has to be greater than or equal to 0, but the denominator cannot equal 0, so we're going to set the radicand of the denominator to be strictly greater than 0. So when I add 3 to both sides, I have 2x is greater than 3, divide by 2, x is greater than 3/2. For this, as long as x is greater than 3/2, it will result in a real number answer when we take the square root. If it is 3/2, then we have a problem because that that would work for the radical. We'd get square root of 0, which is 0, but we'd have a 0 in the denominator, which is undefined. It's not a number. So our domain is restricted that it has to be strictly greater than 3/2, and it can go anything above 3/2 in a positive direction infinitely. So once again, just to summarize this last example, finding the domain algebraically, if you have a fraction, set the denominator equal to 0, and then make sure that you exclude those values. You can see that on my number line and in the interval notation. And that you have those restrictions on your domain, that t cannot equal plus or minus 1. If it's a radical, set the radicand greater than or equal to 0, and then write your interval notation. And if it's a radical in the denominator, set the radicand strictly greater than 0, and write that in interval notation. The 3 cases that you have to be particularly careful for when finding the domain algebraically. We'll be doing some more practice with this tomorrow. Hopefully you were able to follow this. If you'd like, you can look in your book at some additional examples. Again, example 5 from lesson 1.1.